So welcome back friends. Today we'll be implementing self-attention mechanism. So the prerequisite is everyone should be aware of this attention, and so idea of this is not exactly explaining step by step, but rather focusing on the coding part of this particular mechanism, that is self-attention mechanism. So as we all know that this self-attention is nothing but a self dot product attention where we have query, key and value matrix. I like this general analogy of Google search. Consider query as your search query, which is like what you are looking for. Key is like the page title, what each word is advertising, and then value, it is the actual page content. So it tells what each word contains. So here's how we solve it. We do a matrix multiplication between query and key matrix, scale it obviously to stabilize the training, and then apply softmax on top of it, and then again do a matrix multiplication between both of these components. So let's get started and start working on it. So here's the description. Implement the self-attention mechanism, a fundamental component of transformer models used in NLP and computer vision. Your task is to implement self-attention functions that compute attention output given query, key and value matrices. Great. And then we have this formula which we will be using right now, and here is the input, query, key and value, and the output should be attention output matrix of shape, sequence length and dv. So yeah, let's get started. What we want first, let's first check what we already have. We have query, key and value vector, right? So if we have this, what we want is dk, that is to scale this matrix multiplication. So we'll find dk, which is nothing but this axis. So we'll have q dot shape last dimension, because we want shape of this. Then what we want to have scores of attention scores, that is this. So let's find that. Scores equals to, we'll do matrix multiplication q into k dot transpose, and then we'll divide it by np dot sq rt dk. Great. Now apply softmax row wise to get attention weights, which is this part. So let's get started. Exponential scores softmax equals to np dot exponential of scores. Okay, so ideally this is how our numerator of softmax look like, but there's a catch. If we do this and during training, if the scores are becomes very large, this term might explode, and then we fall into exploding gradients problem. So a hack is to subtract max of scores, obviously in that dimension, along that dimension, and we have to keep overall dimension same. So keep dims equals to true. And then what else? Okay, we are yet to complete our softmax. We have the numerator, we want the denominator, so denominator will obviously be, so our total attention weights would be our numerator divided by denominator. Now what was the denominator in softmax? We have e to the power xi upon summation over all e to the power xi's, right? So divided by np dot sum exp of scores, same goes with this, keep temps equals to true, and then what next? We have this. Now we want to compute the output, that is output equals to attention weights into v, right? Matrix multiplication. Now simply return output, run. Okay, what is the issue? Max. Okay, it was skip temps. Now great, we are in the right direction, and then we'll finally submit and check if our solution is correct or not. Okay, here we failed 2.5, 4, 8, 10, 12, 6, 7. Let's check, let's debug where are we mistaking. Dot, and we have np dot square root of dk. Okay, till here we are in the right direction. Then exponential scores, np dot exp scores minus, we are subtracting the max one to stabilize the exponential scores, and then our attention weights, which is exponential scores divided by sum of all. Then we have output equals to attention weights into v, return output. I am not sure what is exactly happening over here, but print output. Oh man, over here we want matrix multiplication. Okay, now let's run once again. Great, now we have corrected this. So this is how we should work. Solve it, check where is the bug, and then move forward. So here by mistake we used star, which was doing multiplication, simple multiplication. Rather we wanted a matrix multiplication, and that's why we used @. So yeah, that's it. Thank you.